All right, hey everyone. I am Alex Korbonits, and I'm a data scientist at Remitly. Tonight I'll be giving a talk called AUC, or Area Under the Curve, at What Costs? And this is going to be a talk about evaluating and comparing between machine learning models when, let's say, you have a data product like a fraud model and deciding which ones to put into production and what some of those trade-offs are when you want to do that. So before we dive in, here's a brief intro about Remitly and me. Remitly was founded in 2011 to change the way people send money home to their loved ones. Worldwide, remittances represent about $660 billion annually. This is roughly 4 times the amount of total foreign aid that governments and NGOs send. So person-to-person transfers represent a huge opportunity for making the world a better place. And now we're the largest independent digital remittance company in the United States. We are sending over $2 billion overseas annually, and we're growing quickly. It's really exciting to see the changes since I started about 18 months ago. Our CEO was recently named one of the Entrepreneurs of the Year for 2016. I realize it's 2017 now, but that was really exciting for us. And I'm Remitly's first data scientist, and our team is growing, which is really exciting. We've got 2 data scientists now and 3 data engineers. My principal focus is fraud classification and fraud modeling. I also do some work in anomaly detection and some other things, but principally fraud classification is what I do. And previously, in my last life, I was data scientist at a startup called Nuku, focusing on natural language processing problems. So today we're going to go over a few things. Model selection is really crucial for delivering successful data science projects in industry. The inclusion of economic constraints and class imbalance issues into this process is often overlooked. If you're simply maximizing area under the receiver operating characteristic curve, you're going to be missing out on these class imbalance issues, especially in fraud, which is basically doing anomaly detection, supervised anomaly detection. You won't pick up on these imbalance issues at all. So industrial settings can require thinking beyond the status quo of model evaluation metrics. And today what we're going to be doing is we're going to consider tying model selection and business costs together to assess their impact. So that makes sense, and it makes dollars and cents to do that. In terms of fraud classification specifically, there's a real penalty of being incorrect. We need to address the economic impact of model selection head on. So you may think that in order to solve all your problems in machine learning, you only need to have big data. Wait. There we go. Big data. Or maybe you think all your problems will be solved with deep learning and neural networks. Even the TV show Silicon Valley mentioned neural networks and machine learning several episodes last season. Be sure to check out the new season. It just started up again on Sunday. So you know this is a really hot area, really exciting. But the thing is, you can do a lot with simpler networks, or simpler models to begin with. And if you keep fanning the flames of AI hype, we're going to create our own AI winter. So please stop with all of the deep learning fixes all your problems. Thanks. You really need to think carefully about model selection. It's not just about big data, it's not just about deep learning, it's about model selection. So you can't just use fancy algorithms to solve all your problems. You need to evaluate your model and compare between them. So we're going to focus on model evaluation and from a supervised classification perspective. So the no-free lunch theorem here tells us that there isn't a one-size-fits-all model class to solve all of our problems. So how do we do model selection? What do we need to incorporate that other approaches do not? It's not just about cross-validation, optimizing our hyperparameters and tuning them, etc. We want to tie models into our business objectives directly. So you may have a problem where the penalty of misclassification varies per instance. Fraud is a great example of this. We are sending transactions of variable size across the world. And so we can't give a per cost penalty to our transactions. Additionally, we can't give the constant penalty per transaction to the model. It just doesn't work out for us. So loss matrices won't work for us here. Let's say that the penalty of misclassifying one transaction is $1,000 versus misclassifying a transaction versus that's worth $10. That's a very different penalty size. And getting the majority class right versus wrong doesn't offer us much in the way of penalties for loss matrices either. So forget about those. In economics, we have budget constraints and utility functions. In other words, we have constraint optimization and we have Lagrangians. Rational individuals in the economics literature maximize their utility subject to their budget constraints. Level sets of their utility functions represent curves of equivalently achievable utility. So here at Remitly, we have transactions, we have revenue associated with completing them, costs of reviewing those transactions, and costs of losing money due to fraud, chargebacks, and partner issues. As a rational individual, as a price-taking firm in a competitive industry, we want to maximize our own utility subject to our economic constraints. So how can we do that? Well, models that need to predict a propensity score or a probability or just some sort of score in general rather than, say, a binary class label. Let's take logistic regression as an example of a model that does this very naturally. These types of models have trade-offs. And these models aren't really one classifier per se. When you have a model like logistic regression that outputs a score between 0 and 1, you really have a continuum of classifiers as you vary your classification threshold from 0 to 1. So each of those thresholds can represent a single confusion matrix across the different thresholds. So selecting the right model, which in the case of logistic regression means selecting the right threshold, will give you your optimal confusion matrix. In fraud, it's extremely expensive if it occurs, but it's also painful for customers to be put into review too easily. So you do care a lot, and you care differently about type 1 and type 2 errors. When fraud is so infrequent, it might be easy to say, let's just review everything, and we'll catch all of them. But the negative customer experience, even though from an economic perspective, you won't lose all the money, you might actually lose more in lost customer business if they were to come back to the app. So let's go into my curve is better than your curve. The receiver operating characteristic, or ROC curve, was developed during World War II for detecting enemy objects in battlefields, which I think is pretty awesome. This curve is useful because it offers a description of the predictive power of a model or set of classifiers across all of their different thresholds. So it gives an indication of the kinds of trade-offs you can expect to make by choosing a particular threshold or one model versus another, which is super useful. Another useful curve is the precision and recall curve, which is what our preference is for selecting fraud models at Remitly. Precision and recall are affected by class imbalance, unlike ROC. So that's important for us because class imbalance is such a pervasive state of the domain of fraud. Precision and recall is just as useful for comparing models as ROC, but there are some important differences which we won't go into here. So let's talk about costs. Here's an example in ROC space. What's an indifference curve? It's called indifference because all of the points along the line are equivalent. It's a level set of trade-offs in ROC space. So here we have the indifference curve represented by the blue line. And we also have the curves in green and orange representing the ROC curves for two models in this space. One whose AUC is greater than the other. as we can see, the green classifier has worse performance, but the green curve actually satisfies our constraint. It actually crosses through our indifference curve, which is super exciting because this indifference curve is telling us where we can begin to make a profit as a business. If we're at a point along the ROC curve, which means if we've chosen a threshold for our model that's below this indifference curve, we're going to be losing money. But if we choose a point on this green curve for the threshold of our model that lies above the blue line, we're in business. This is great. We can keep the lights on. So your confusion matrix is going to have different costs depending on which quadrant of your confusion matrix that you're in. Your costs are going to define the slope and intercept of this indifference curve in ROC space or precision and recall space. And it doesn't even need to be a linear set of costs either, even though we're using a linear example here. You need to have a model with a set of thresholds that crosses this curve for your business to make sense and put your model into production, importantly. What's so great about this is that incorporating business sense into our model selection helps us choose between these models, not only in isolation, where the model with higher area under the curve seems more attractive, but when we want to put into production, we need to make sure that the model we're using actually makes business sense. So we actually do want to deploy the green model here. So back to precision and recall space. Now that we have a model that's economically viable, the green model from the previous slide, how do we choose the right threshold? One way you'd want to pick a threshold, find the maximum point in the direction perpendicular to the indifference curve that your classifier can achieve. So this is the highest level set that you can achieve with your classifier. Here in precision recall space, we have two models that satisfy our constraints. Both the red and blue curves cross our indifference threshold. It looks like your curve actually wins out in the bottom right-hand corner. Even though the area under the PR curve is significantly greater for my curve, your curve has a set of points farther from our indifference curve. And therefore, picking a threshold to use for classification out here will be better if we use your model instead of mine. Said in economic terms, we're at a higher level set, and you'll be able to make a greater profit if you pick a point out here on the red curve. So, said in another way, in the language of confusion matrices, the weights and costs of false negatives are so high in fraud that we really need to have high recall. That's why this indifference curve is not only so steep, but also so far to the right. We need to catch, let's say, 90+% of all of our fraudulent transactions to even stay afloat. Whereas the precision doesn't really need to be as high. We just really need to catch those transactions and have high recall. So your constraints may not be linear, and they may change with time. So if you are implementing a framework like this to compare and contrast models, you may need to not only evaluate the thresholds you're picking at a frequent basis, but also the business logic for costs may change as well. And in summary, model selection is super important. Maximizing area under the ROC curve is great, but may not be the only metric that you want to consider when choosing between two models. For us, in fraud, there's a real penalty of being incorrect. We have to incorporate cost into model selection. It's not an option for us to do otherwise. And we are just getting started. We are not done with this analysis. We're doing post-training analysis of costs and different model metrics such as ROC and PR. We're also looking into incorporating business objectives into the loss functions directly for our learners during training. This is part of our Q2 OKR process, and it's pretty exciting to see where we're going with this. So what does machine learning ultimately look like? Well, on the one hand, it's about fraud classification and anomaly detection. On the other hand, it's about customer behavior, market forces, understanding customer lifetime value, pricing optimization. There are a whole host of exciting decision sciences problems that we like to think about and work on every day. And we're hiring. So if you're interested, please reach out. And that's all I've got for tonight. So thanks so much for coming out, and I hope to see you all again at the next meetup.